Yeah.
All right. It's my great pleasure to introduce Victoria Knopova from Kyiv National University. And the title of the talk is on simulation of Levy processes.
Yeah. Thank you very much, Amir. Thank you very much, Yana, for this opportunity for me to give a talk on this conference. I really appreciate it. And today I will talk about the new research with two co-authors, with my colleague from the University of Dmitry Ivanenko and my PhD student, Denis Platonov, who is also here. And I will speak about approximation of Levy and Levy type processes. So at first, I give you some introduction and the motivation of why we are working why we are interested in this approximation, why we think that it will give us some nice results. And then I present you some results, and in the end, I also show you some numerics. So just to set the notation, and what is the infinitely divisible random variable? It's a random variable which for any fixed n we can decompose in a sum of identically distributed random variables as at I, and we are lucky to have the Levy-Kinchir representation for the characteristic exponent of that. So here is the Levy-Kinchir representation. Here, nu is as usual the Levy measure, which means that we can integrate a minimum of 1 and u squared. L and q are some parameters. So the drift and q corresponds to the quadratic part. And as we all know, there are two extreme cases of infinitely divisible random variables. They are normal a random variable and compound Poisson random variable. So in this case, the parameter of the compound Poisson random variable is the whole mass of the Levy measure. And as we all know, they're intrinsically connected with Levy processes, which are the processes with stationary independent increments. And for all partitions of the interval 0t, and we can decompose a z of t in such a sum. And these parts are independent, and if the case, if this mesh is uniform, so the sizes are the same, then these parts are also identically distributed. Again, we know the characteristic exponent, and again, we have two extreme cases, the Brownian motion and the compound Poisson process. This shows that if we want to simulate a Levy process, by which I mean the trajectory of a Levy process, we need to know how to simulate infinitely divisible random variables. If we know how to do this, we can get the trajectory. So we write here a kind of the Euler scheme, and we can step by step simulate infinitely divisible random variable. So this is the value of our Levy process at point g delta. The problem is that in principle we cannot, we do not have usually the algorithm for simulation Levy process, or we do not have usually the algorithm for simulation of infinitely divisible random variable. Why? because usually we don't have the transition probability density, so we don't have a probability measure. And on the other hand, if we want to get the trajectory, we have problems because a Levy process has countless many small jumps, and we cannot simulate countless many. We can only get finitely many small jumps. So we need somehow to cut the trajectory into parts which we can simulate and which we can drop. Luckily, we have the Gnedenko-Kolmogorov theorem, which says that if we have an infinitely divisible random variable, we can get it as a limit of a normal random variable and a compound Poisson random variable. And so the natural idea when we simulate an infinitely divisible random variable is try to find a sequence of compound Poisson random variable and normal random variable which can approximate this infinitely divisible one. And in principle, we can do the same for all the processes. And so the idea is to try to simulate a Levy process, and later on I will also tell you a little bit about Levy type processes. The idea is to get the trajectory by approximating the trajectory by a normal random variable with some weight, which is t-dependent. Yeah, in this case, I'm saying about the variable of a process at point t. But if we simulate the trajectory, we can get it by the error scheme, and at each step we simulate an infinitely divisible random variable, but its distribution is dependent on this time moment at which were the previous step. So how can we do this? We are lucky to have a Levy-Ito representation. And this Levy-Ito representation is actually the key how one gets the approximation of the trajectory. So just to recall what is the Levy-Ito representation. So if we introduce the counting measure, so we count the jumps of a Levy process which are of size b. So this gives us the jumper measure. If we take the expectation of this measure, we get just the Levy measure of our Levy process, or of our infinitely divisible random. I'm sorry, here it should be t, because we are talking about the process. So here is nt, and here we should have also t multiplied by this in OP. So we can write the representation of the trajectory of a Levy process. And this idea that we can write this kind of representation is behind the early approximation, which are due to Bondesson, and yeah, the representation of Bondesson was for infinitely divisible random variables. For Levy processes, it's known as the Asmussen-Rosinski approximation. And the construction of this approximation is the following. So we cut away small jumps at level delta. And this way we get the first order approximation. And then if we want to get a better representation, we substitute this compensated small jumps. So we cut small jumps and we glue the compensator to the drift. And the part from 0 to delta, we glue to the parameter at the Brownian motion. So the second order approximation has the following form. We have jumps bigger than delta, and we have the starting point, we have the compensated drift, and we have the Brownian motion, but with a bit different variance. And this is fine. This approximation works. There are some numerical implementations of this method, and this method is already more than 20 years old. But we are interested in some refined approximation. Now I explain you why we are interested in this. In the old paper with Alexei Kulik, we studied the transition probability density estimates for Levy processes, and later on we constructed the transition probability density of a Levy type process. And both these approximations use the following structure. In the Levy case, we write the transition probability density of a Levy process in such a form. This is the so-called zero-order approximation. So we cut the Levy measure at some level tau of t, and we take the inverse Fourier transform. So in principle, this part can be viewed as infinitely divisible, as a characteristic function of infinitely divisible random variable, but now we have t as a parameter. So it's no longer time homogeneous if we are talking about a process. And this Q part, it corresponds to the compound Poisson process with this intensity. And then when we get estimates, we estimate essentially this zero-order approximation, and then we approximated this kernel. If we read this approximation in a different way, we have the following. We have in our trajectory the small part and the big part. But when we try to simulate, the small part is nearly impossible to simulate because in this part, Levy measure is bad. And when we simulate, we either throw this part away or we substitute it by something which is easy to simulate. So, for example, the idea is to substitute the small part with a normal variable, but with some mean and some variance. And then we would get the representation of this form. So this part one can try to simulate, and this is our replacement for the small jumps. And sorry, what is this? Oh. This idea can be developed later for the Levy type setting. In the Levy case, we have a Levy triple, which is independent of our current position. In the Levy type case, our next jump depends on our previous position. So here the Levy triple is x dependent. And if you can get a process with this Levy type triple, which is a special problem, one can construct a Levy driven SD, or one can try to write the parametrics problem for this Levy triple. And we did this in the series of paper with René Schilling, with Alex Kulik, and with Krzysztof Bogdan and Paweł Sztomek. If we can get the process, this process has also this Levy ether representation. And now this n is the jump measure which counts the jumps of our process of certain size. And if one tries to get the transition probability density, I mean the estimates of the transition probability density, assume that this density exists. The approach for this is similar to the Levy case. And we have some zero order approximation. Don't worry about this function. Theta is just some shift which is due to the drift which is present in the Levy triple. And this Q measure is the compound Poisson type kernel. So the structure in the parametrics construction is pretty the same, which is in the Levy case. We have some zero order approximation, but usually we cannot get the simulation for the zero order approximation. What we can try to simulate this big jump part. And when we construct this big jump part, we don't use a fixed level carton as it was done in the Asmussen and Rosinski approximation. In the construction, we need to cut the Levy kernel or the Levy type kernel in the Levy type case in the time-dependent way. So what I want to say is that this dynamic cutting naturally arises when one tries to approximate the transition probability density of a Levy process or of a Levy type process. And yeah, so now I come to the notation and the result. I need a few assumptions. The assumptions we have are the assumptions on the tail functions of the Levy measure. So we have the Levy measure. Nu plus and nu minus are the restrictions of the Levy measure to the positive and negative half line, and we invert these functions. In order to invert, we assume that this kernel is good. So which means that n plus and n minus are strictly monotone and continuous. And under this assumption, we can invert them and get this function tau plus minus. We also need some regularity of our Levy measure nu. And we pose regularity assumptions on positive and negative lines separately. For this, we introduce the so-called Pruitt functions. So Pruitt functions are these two guys. This is the lower function, this is the upper function, lower and upper, because this is smaller, this is bigger. And the upper function is actually the sum of our kernel and the lower function. The regularity assumption we need is that these two guys are comparable. And actually, the same type of assumption was used in the papers with Skulik for the estimates of the transition probability density. So this is kind of the assumption of regularity which we need if you want to get the compound kernel estimates. So what we do here, if our jump size is fixed, then we cut away from the Levy kernel this area. If our jump size if we want to do the dynamic cutting, we cut away this blue area inside. So we consider only the jumps which are bigger than tau plus or smaller than tau minus. And then if we cut these areas, we have our first and second order approximations. So the first order, we just cut these big jumps or also small jumps. So we cut the jumps which are in this blue area. We consider only the jumps here and here. And these two processes are essentially the compound Poisson processes, but they're timing homogeneous. In this case, the jump sizes are also time dependent. This is a disadvantage when we want to simulate the trajectory. But if we want to get the value of a Levy process at a fixed point t, then in principle, it doesn't hurt. The good point is that the intensity of this compound Poisson process is good. It's independent of whether we are on the positive half line or negative half line, and it's pretty simple. So if you want to get the second order approximation, we do the following. We consider the difference between our Levy process and the part which we already have thrown away. So these are our small jumps. And the idea is to show that these small jumps are comparable if t is fixed to the to the normal variable multiplied by some time-dependent constant. What we need for this, we need the estimates on the moments of the Levy measure on the set. These estimates on the moments are not very difficult to get. For this, actually, we need these two initial assumptions. So if you have this assumption on the regularity of the Levy measure, and then we can show that the p moments of our Levy measure, so we need p moments of such a form, we can estimate these p moments for p bigger than 2 from above, and for p equal to 2, we can even get the lower bound. Here we have some negative power, but don't worry, if this part is small, it tends to 0 when h is tending to 0. So this parameter h here, and I just want to say a few words. This parameter h here is some kind of tuning parameter. So we make this h small in order to approximate our value of z. And the parameter epsilon is needed to have the intensity of the compound Poisson to be finite. So if we just take this epsilon to be 1, this integral is infinite. And we want to have the compound Poisson with finite intensity, of course. So otherwise, it's not compound Poisson. So now I show you the weak type estimates we got.
I'm sorry, it was about 5 minutes left.
Yes, I know. I don't show the proof. I just show this result and then show the simulation. So in the Levy case, we have these types of weak estimates for the first order approximation, for the second order approximation. You see that for the second order approximation, it's a bit better. Here we have logarithm. Here we have just h to some negative power. And essentially the same idea is translated to the Levy type case. So essentially one can write, I think I show the result in the Levy type case. So in the Levy type case, we have the same type of estimates, but here the power in the second order approximation, we don't have a logarithm. We have also h to some negative power, but we can make this negative power arbitrarily small. I think I say just a few words about the proof. The proof is based on 3 milestones. So we need to use the essence theorem for the approximation of. I just show the essence theorem. We need the essence theorem in order to show that the small jump part can be approximated by a normal variable. So we show that if we normalize the small jump part, then the distance between the probability measure of the small jump part and the probability a function of the normal variable is small, and then essentially we can estimate this type of probability. And in order to apply the essence theorem, we need to apply the Burkholder-Davis-Gandy inequality in order to get the moments of this random variable. I think in the end, I show you how it can be done in practice. Here I show you the results when we simulated the alpha stable random variable, just a schematic alpha stable. And we simulated the p moments. As you know, we have in this case the p moments of the order smaller than alpha. And we simulated this p moment by Monte Carlo using our approach and using the approach of Rasmussen and Rosinski. And in principle, you can see that the dynamic cutting gives better results because we cut in a more careful way. So our moments are in principle more close to the original than the results obtained by the as a fixed cutting. And this is even more visible if we estimate the distance between the characteristic functions. In this case, if we simulate the empirical characteristic function, and if we compare it with the true characteristic function. So here you can see the numerical results which are due to my co-authors. And you can see that the difference in this method between the true characteristic function and the empirical characteristic function in our case has significant different order than if we use a fixed if we use a fixed level cutting. So here we have the order 10 minus 3, and here we have actually much better difference. So at the moment, we have only results for the Levy case. In the Levy type case, there is, of course, a problem because we need to use the error scheme to simulate even the value of a Levy type process at the endpoint. So even if you want to compare the results of our approach for the value of the process at the fixed point, we need to come to this fixed point, and for this we need the error scheme. In the Levy case, we essentially compare here the difference between the characteristic functions of one infinitely divisible random variable and its approximation. In the Levy type case, it's more complicated because the next jump depends on the position, and we need to get the whole trajectory in order to come to the endpoint. So this is our future program, and I want to thank you for your attention. That's it.